warahmatullahi wabarakatuh. So you are welcome to another episode of our online classes. Today we want to look at the experiment to determine the specific heat capacity of solid by method of mixture. The experiment to determine the specific heat capacity of solid by method of mixture. You can still recollect our last class. We talked about the experiment to determine the specific capacity of liquid or solid by electrical method. So today we want to look at another method entirely, which you can use to determine the Sh of a solid. Now, before I proceed, this experiment, this method of mixture can also be used to determine the specific capacity of liquid. Not only you can use to determine the Sh of solid, you can also use it to determine the specific capacity or heat capacity of liquid. Now, in method of mixture, we employ the use of a certain apparatus, and that apparatus is called calorimeter. That apparatus is called calorimeter. This is a typical example of a calorimeter used in the laboratory. A calorimeter is an apparatus used in the experiment that involve the exchange of heat between two bodies that are at different temperature level. I repeat, a calorimeter is an apparatus or device used in the experiment that involves the exchange of heat between two bodies that are the different temperature level. Now, what are the component parts of this calorimeter? Now, first and foremost, this calorimeter can be made of a material of copper or aluminum. It can be a material of copper or aluminum. That is, you can have copper calorimeter or aluminum calorimeter. Now, we have the various component parts of a calorimeter. We have the lid. This is the lid, the cover. You can see that the cover is made of plastic. That is an insulating material. Now, we have a particular hole here. It has the lid has a particular hole here. This hole is meant for us to insert our thermometer. This hole is meant for us to insert our thermometer. Anytime we want to use thermometer to measure the content, the temperature of the content of the calorimeter. And again, another component we still have here, or another part, the component part of this calorimeter is the calorimeter has the inner and then the external part. The inner part is this, where we are going to have our mixture. Don't forget, we said we are using the method of what? Mixture. So this inner part will contains our mixture. That is, the mixture will be the liquid we are to use, the metal solid we are still using, and some other materials, including the stirrer. So this stirrer will still be inside this inner part of the calorimeter. And again, it has the external part. This is the external part. But between the inner part and the external part, there is a separation between the two. That is, there is another material that we use to prevent the contact between the inner and then the external part. So this material is usually made of a very good insulating material. A short example of that is cotton wool. So if you see this thing, this looks more or less like what? Cotton wool, because the perfect example of what? Insulator. And the essence for a typical calorimeter to be effective, so it must be lagged. What do we mean by lag? That is, it must be properly insulated so as to prevent heat loss to the surrounding. And there is the main excess the main essence of what? Of this insulating material that is separating the inner and then the external part of the calorimeter. So it prevents the heat loss to the surrounding. And again, as this calorimeter, as we have it, even though we said it must be properly lagged, that is, it must be some certain material, some insulating material must be used to prevent the heat loss to the surrounding. But even with that, there is still the tendency for heat energy or heat being lost to the surroundings. No matter how we prevent or how we try to prevent the heat loss to the surrounding, we still have a way in which it can still be lost to the surrounding. And in what ways can it be lost to the surrounding from the calorimeter? One, it can be lost through the process of radiation. It can be lost through the process of conduction. It can be lost through the process of convection, and even through the process of what? Evaporation. And each of these component parts of the calorimeter try to prevent the heat loss in one of all the methods that are already listed. Now, for instance, this plastic container, the end of having a plastic container here is to prevent heat loss to the surroundings by the method of evaporation and conduction. To prevent heat loss by the method of what? Evaporation and either conduction or convection. Now, the function of the insulating material that we have inside the calorimeter, which is this cotton wool, this larger material or insulating material, this cotton wool that separate the inner and then the external part of the calorimeter, is also to prevent the heat loss to the surrounding through the process of conduction. Don't forget, if we just use ordinary metallic material, say only the external part, this core, this container, the external part of the calorimeter, without using the insulating material and then the internal part, we only want to use this. What is going to happen is that by the time we introduce hot liquid or hot substance inside this, and then you cover it, by the time you touch the outside, the outer part of this container, you discover that it's going to feel hot. Which means the heat has been transferred from the hot substance that we have inside it into the surrounding part of the calorimeter. And in that case, there is tendency for heat energy to get lost. And in that case, in order to prevent such heat loss, then we use this cotton or the insulating material. Then we now have another inner part, which is so this is what we call the calorimeter. And then we mostly use this calorimeter in the experiment involving the determination of specific capacity of substance through method of mixture. Now, what do we call the method of mixture? Method of mixture involves a situation in which, as the name implies, it involves a situation in which you have some substances being mixed up together. And in the process of mixing all these substances together, we have the hot or the hotter substance, and then we have the cold, the cold substances. And by the time we now mix the hot and then the cold substance together, there is tendency for heat energy to be exchanged or to be transferring from the hot substance to the cold substance as a result of this mixture. So that's what we call the method of mixture. And let's now look at what this experiment is all about. Now, how do we now use the experiment to determine the specific heat capacity of solid? The first thing we need to note here is that if we want to use this experiment to determine the specific capacity of solid, the liquid we are going to use must have a known value of specific heat capacity. For instance, I want to determine the specific heat capacity of solid metallic brass, which is this, or solid metallic copper. We are given a solid metallic brass or copper as a solid. Then that solid is unknown, is of unknown specific capacity, but we want to determine its specific capacity. We are going to use a certain liquid in the process, and such liquid that we are going to use must have a known value of specific heat capacity. But let's assume that we want to use the same method to determine the specific capacity of liquid. Now in this case, the solid metallic material we are going to use must be of known value of specific heat capacity, and the liquid we want to determine specific capacity will be of unknown SHC. Here we want to determine the SHC of solid. Then we are looking for the SHC of solid. That's why we say solid of unknown SHC. But the liquid we are going to use we must know its specific capacity, which means if I'm to use any liquid now, I will use water, because water has a specific capacity of what? 4,200 joule per kg. Not that the solid we want to calculate the SHC of solid, and at the same time we are still using the liquid that is of unknown SHC. There's no way we can easily calculate for the SHC of that solid. So when we want to calculate the SHC of any particular solid, then we use liquid that has a known value of what? Specific capacity. Now let's begin. This experiment, we want to perform this in the laboratory. What we just need to look for, we need to look for our source of heat. Our source of heat can be stove. A very perfect example of our source of heat in the lab is what? Stove. So don't forget, we can still use other sort of heat. It can be electrical heat energy or some other means. But majorly we normally use a stove in the laboratory. Then we look for a container in form of pot, small pot, and this is it. Inside this container we have liquid, which is water. The solid that we want to determine is specific capacity. We put it inside this container that contains a certain volume of water. Then we start heating it. Now the initial temperature of this water is not needed yet. We have thermometer here. The thermometer is just for us. The function of this thermometer is to use to check the temperature of this boiling liquid or boiling water. Now, if we allow this water to boil for some minutes, or we allow the water to boil at exactly 100 degrees Celsius, or very close to the boiling point of water, which is 100 degrees Celsius, then you can use our thermometer at that point to check the exact temperature of that boiling water. So if the exact temperature is checked, but we make sure that that temperature of boiling water is very close to the boiling point of water, which is 100 degrees Celsius. It might be around 90, 95, 98, or even 100 degrees Celsius. Now we record the value of that temperature of the boiling water. We record it down. If it is 90 or if it is 100 degrees Celsius, that is the temperature of the boiling water, and that also serves as the initial temperature of the solid substance or solid material that you want to determine its SHC. And another thing that we still need to do now is, after we've boiled this solid for that particular period of time, then we will have prepared our calorimeter. We will have made our calorimeter ready, which is this, the next diagram. Which is the next diagram? That second diagram, yes. Now, this is our calorimeter. As you can see, like the one I just shown to you now, this is our calorimeter. It must be lagged. This is what we call the lagging material. Lagging material. That lagging material can be wool, cotton wool. Now, this calorimeter, we now try to add a certain volume of water. Don't forget, I said the liquid we are going to use here must be of non-specific capacity. That's why we are using water for this experiment, because we know the specific capacity of water to be 4,200 joule per kg per Kelvin. Now, the calorimeter has a stirrer. We also have a place to insert our thermometer to check the temperature of the mixture. Then we have our metallic solid. And what's going to happen here is that after we've allowed this solid to boil for about 100 degrees Celsius of temperature, we quickly, I repeat, we quickly transfer this solid, this boiled or hot solid metals. We transfer it quickly to the calorimeter containing a certain volume of water. But before we transfer this solid to this calorimeter, we will have measured the initial temperature of the water in this calorimeter. Where are we going to put that water in the calorimeter? Inside the inner part of the calorimeter. As we have the inner part of the calorimeter, we try to fill this small container of the calorimeter. Maybe we fill it about 2/3 filled with water, or half of it filled with water, as the case might be. If we fill this with water, then we measure the initial temperature of the water inside this calorimeter. We record the value of the initial temperature there. Now, initial temperature of the water in this calorimeter also give us the initial temperature of the calorimeter itself, which means the initial temperature that we measure for the water is also equal to the initial temperature of the calorimeter. That is before we transfer the hot solid metal to this calorimeter. Now, after we've now determined the initial temperature of the water and the calorimeter, then the next thing is to determine the mass of water in the calorimeter. How do we determine the mass of water in this calorimeter? Provided that the mass of water in this calorimeter is not given. But if we've already known the amount of water inside this calorimeter, then you just record the value down. But if the value is not known, we just put a certain volume of water, a certain mass of water in this calorimeter. We don't know the actual amount of that water. But what we just need to do to know the mass of that water is that before we introduce water in this calorimeter, we first weigh our calorimeter, everything. We weigh everything. We weigh it while empty. We weigh this calorimeter. We weigh it while it is what? Empty. While it is empty, when it contains nothing, we weigh it and then we determine its mass. So we can weigh the whole of this together with the stirrer, everything. We weigh it. We weigh this calorimeter and we record the value as we can record the value as we record the value as M2. We record the value as M2 because our M1 will give the mass of the solid. We will have used the beam balance or chemical balance to determine the mass of this solid. So we record the mass of the solid as M1. It might be in gram or in kg. If you measure it in gram, then you convert it to kg. After then, we measure our calorimeter together with the stirrer when it is what? Empty. We record that value down to what? M2. Then we now fill this calorimeter, maybe 2/3 or half of it with water. We now reweigh. We will discover that new measurement will be more than M2 because our M3 now has additional value of water, which is having another mass. So being added to what? To M2, giving us M3. So if you want to determine the mass of water in the calorimeter, the mass of water will now be M3 minus M2. That is, we subtract the empty mass of the calorimeter from the mass of the calorimeter and the water. So that's how we determine the mass of the water in the calorimeter. Now, after we've measured all those things, then we've heated our solid to about 100 degrees Celsius. The next thing is to quickly transfer this solid quickly without allowing it to get lost to the surroundings in the process of transferring this solid to the calorimeter, because that one might affect our calculation or the value of the SHC of the solid that we want to calculate. Then we transfer this solid to this calorimeter quickly, and what we now have the stirrer inside the calorimeter. We have the metal solid in the calorimeter. We have the water that's been half or 2/3 filled in the calorimeter. That's more reason why we call it the method of what? Mixture. Why do we call it method of mixture? Because we have the water, we have the metal solid being inside the same container, which is what? Our calorimeter. Now in this case, the water initially is cold. Why the metal solid that we are bringing in is hot? Bringing hot object and cold object together, what happens? There will be a transfer, or there will be an exchange of heat between the two bodies. Don't forget, heat energy always flows from a region of hotter temperature to a region of what? Lower temperature. Which means that the heat energy is going to flow from the hot metal solid to what? To the water inside the calorimeter. Then we have the stirrer. What's the function of this stirrer? The function of the stirrer is that by the time we have this hot metal solid in this container, and then we close it using the lid. Then we continue using this stirrer to stir the entire mixture. This way. We use the stirrer. We won't open the lid. So we won't open this cover or the lid. We just use this stirrer. This stirrer is inside the inner part of the calorimeter. Then we use it to stir the mixture or the content, that is the metal solid, the water inside it, everything. We stir it. The essence of stirring that content of the calorimeter is to allow for even distribution of it. Which means that it will be very difficult for one side or one part of the water to get hot and the other part of water to get cold. And that is what's going to happen if we do not stir the mixture continuously. So stirring constantly allow the even distribution of heat. Then we allow that to take place for about 2 to 3 minutes. And in that case, some part of there will have been an exchange of heat between the hot solid metal and the water. Then the temperature of that water will be changing with time, because there is direct contact between the water and the metal solid. Now a point will be reached in which the temperature of the water, which is initially cold, and the temperature of the metal solid, which is initially hot at 100 degrees Celsius, a point will be in which the temperature of these two substances, the metal solid and the water, will be equal. We call that point, we call it the equilibrium point. That is, at equilibrium point, the heat supplied by this metal solid will have equal to the heat gain by this water. But another thing that can also happen is that it's also possible that some part of the heat being supplied by this metal block is not solely absorbed by the water, but also absorbed by the calorimeter itself, which means in that case, at equilibrium, the total heat lost by this metal solid will be equal to the sum of heat absorbed or gained by water and the calorimeter. So that is the major process or the method by which you can use to determine the SHC of that solid. So in this case, the final temperature of the at equilibrium we now use this thermometer to measure the final temperature of the mixture. Don't forget, the final temperature of the mixture will be the temperature of the metal solid and the calorimeter and the water. 3 things now. The final temperature will be the temperature of the solid, the water and the calorimeter, while the initial temperature of the water will be our θ1, which is initial temperature of water and calorimeter. But the initial temperature of the metal solid would have been determined from here. That's the temperature of the boiling water. So let's now see how we can calculate the specific heat capacity of that metal solid. So let's check how we can calculate the specific heat capacity of that metal solid. So let's see. Now the specific heat capacity of solid is calculated as follows. Mass of solid. Don't forget I said we are going to record the mass of the solid. We use our beam or chemical to measure the mass of the solid, then we record it as M1. If the scale we use is in gram, then we convert the value to what? To kg. We also determine the mass of calorimeter and stirrer. I told you that when this calorimeter is empty, we measure it in gram, then we convert the value to what? To kilogram. Then mass of calorimeter plus stirrer plus water. After we now fill the calorimeter, about 2/3 or half filled with water, then we weigh this calorimeter and its content. We weigh the calorimeter and its content. So we now record the mass that we what? N3. Don't forget to determine the mass of the water to determine the mass of water, we just say mass of water inside this calorimeter will be N3 minus M2. You subtract the mass of calorimeter and stirrer from mass of water, from mass of calorimeter, stirrer and water to give mass of water. Then we record the initial temperature of water and calorimeter, and that is theta1. Final temperature of mixture. That is, final temperature of mixture is after we've transferred the hot metal block into our calorimeter. So in that case, the final temperature, which is theta2, will have been greater or more than the initial temperature of water and calorimeter, which is theta1. And we also determine the temperature of boiling water, which is theta3. The temperature of boiling water is directly or indirectly the value of what? The value of the temperature of the solid metal block is the value, that is, this theta3 is the temperature or the initial temperature of the metal solid block that we are looking for its specific heat capacity. Then the specific heat capacity of solid is represented by C. Also, the specific capacity of water is represented by 4,200 joule per kg per Kelvin. The specific capacity of water equal 4,200 joule per kg per Kelvin. While the specific heat capacity of calorimeter material is C2. The specific capacity of calorimeter material is C2. Now, let me say this. If we are using, because we have different materials with different specific capacities. For instance, a copper materials, we have a specific capacity of copper. An aluminium material, we have a specific capacity of aluminium. Now, if the calorimeter we are using, is copper, therefore the specific capacity of this calorimeter will be that of copper, which is 390 joule per kg per Kelvin. If the calorimeter is aluminium, then we use the specific capacity of aluminium for that calorimeter. Now, heat lost by solid in cooling from 100 degrees Celsius to heat lost by solid in cooling from 100 degrees Celsius to final temperature of mixture, which is theta2. Heat lost by solid in cooling from 100 degrees Celsius to final temperature of mixture, that is theta2, is given as. So how do you calculate the heat loss? Don't forget that in this process, one material is going to lose heat and some materials are going to gain heat. Which material is going to lose heat? That is, the hot metal solid that we transfer into the calorimeter is going to lose heat, and which material, which substance is going to absorb it. The water in the calorimeter and the calorimeter itself are going to absorb it, and at equilibrium the total heat lost by that solid metal block will be equal to the total heat gain by water and the calorimeter. At equilibrium, the total heat lost by solid will be equal to the total heat gain by water and the calorimeter. So in this case, the heat lost by solid will now be mass of the solid, which is M1, times specific heat capacity of solid that we are looking for. Specific heat capacity of solid, which is C, that we are looking for, multiplied by change in theta, that is temperature rise of the solid. That temperature change of the solid will be, the two temperature changes of the solid are the temperature of boiling water, which is theta 3, and this theta 3 might be 100 degrees Celsius. That's temperature of what? Boiling water. Now, and the second temperature value of the solid is the final temperature of the mixture, which is what? Theta 2. So I will have this one to be theta 3 minus theta 2. I will have it to be theta 3 minus theta 2. So if my theta 3 is 100, that is the temperature of boiling water is 100 degrees Celsius. So I will have 100 minus theta 2. Now, let's look at the heat gain by water. We're going to need the expression for heat gain by water. The heat gain by water will be the mass of water. The mass of water. The heat gain by water will be mass of water. Will be mass of water times specific capacity of water and temperature change of water. Mass of water times specific capacity of water times change in temperature of water. Or let me use, because it's like that side is not that clear, so let me use this side. Let me use this side. So the heat gain by water gained by water equal mass of water, and mass of water will be M3 minus M2 times specific capacity of water, which is 4200, times change in temperature times change in temperature of water. The change in temperature of water will be, those two temperature values of water are the initial temperature of water and calorimeter, which is theta 1, and the final temperature of the mixture, which is theta 2. And in this case, theta 2 must be greater than theta 1. So I have theta 2 minus theta 1. I have theta 2 minus theta 1. That is mass of water M3 minus M2 times 4200 times theta 2 minus theta 1. So that's the heat gain by water. Then heat gain by calorimeter. If we are told that the calorimeter also gain heat, so heat gain by calorimeter will be mass of calorimeter, which is M2, times specific capacity of calorimeter, which is C2, times change in temperature of calorimeter, which is theta 2 minus theta 1. So change in temperature of calorimeter is always change in temperature for water, which is theta 2 minus theta 1. Now, in this case, therefore, at equilibrium, heat gain equal heat lost. So total heat lost by the solid, heat lost equal total heat gain. Heat loss equal total heat gain. and my heat lost equal M1 times C theta 3 minus theta 2 equal heat gain by water M3 minus M2 times 4200 times theta 2 minus theta 1 plus, that is this one plus, is better I write it complete so that it won't confuse you. So let me do this plus this heat lost by the solid equal heat gain by water plus heat gain by calorimeter, and heat gain by calorimeter is M2 times C2 times theta 2 minus theta 1. Because we are looking for the specific capacity of the solid, then I will make my C the solid formula. Making my C the solid formula, we have C equal the whole of this M3 minus M2 times 4200. Now, I want to factor out theta 2 minus theta 1 from here. I want to factor out theta 2 minus theta 1 from there, because theta 2 minus theta 1 is common. Theta 2 minus theta 1 is common to water and calorimeter. So factoring that one out, I will have M3 minus M2 times 4200 plus M2 times C2 into this open bracket multiplied by theta 2 minus theta 1, or if you like, you can do it one after the other. So all this over mass of the solid M1 times change in temperature of the solid, which is theta 3 minus theta 2. So that is how we add the unit is going to be joule per kg per Kelvin. 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 So that's how we determine the specific heat capacity of solid by method of mixture. So I said we can also use the same method to determine the specific capacity of liquid, and in this case we use solid of no specific capacity. What we are going to do in this experiment is that we repeat the same thing. We repeat the same process, but here, looking at this equation, we have mass of the solid times specific capacity of the solid. This solid we have a non-specific capacity. Change in temperature for the solid will be known. Now come to that of the liquid. Say I want to determine the specific capacity of water now. That I don't know, initially I don't know that the SI of water is 4200. Then I want to find the specific capacity of water. What I will do is that I can use C water, C subscript W to represent the specific capacity of water. Then I will have the mass of water times the specific capacity of water that I don't know times change in temperature of the water plus mass of the calorimeter times specific capacity of the calorimeter times change in temperature of calorimeter. Then because I'm looking for the only unknown value, the only unknown parameter in this equation will be the specific capacity of that liquid or of the water. Then you make it the Soviet formula. So that's how you can use that method to determine the specific capacity. So in this case, after the whole experiment, we need to take something into consideration for our calculation to be efficient. And what are those precautions that we need to take into consideration? Now, one, we have some precautions to take into consideration. One. Precautions. While performing the experiment. And what are those precautions? So, one, 1. Precautions. 1. The calorimeter should be properly lagged. The calorimeter should be properly lagged. I think you know the meaning of lag. Properly lagged. That is, it must be properly insulated. The calorimeter should be properly insulated or lagged. And 2, the hot metal solid must be quickly transferred to the calorimeter. And 2, the hot metal solid must be quickly transferred to the calorimeter. And 3, the mixture must be stirred continuously. The mixture must be stirred continuously. So these are the precautions that must be taken into consideration in order to have a very perfect and correct measurement. So here we come to the end of today's class. So our next class we are going to look at 1 or 2 examples on how you can calculate for the SHC of either solid or liquid. I remain your Malam Salakot Nagminde. Bye for now.